Okay, the items we're going to look at now don't ask you to make the graph of a function given its parent function, but they do ask you to describe what that sequence of transformations would be. So here the parent function f of x equals x squared, and a related function in that family, g of x equals 3 times x minus 2 squared. So all we're really asking you to do here is describe what the sequence of transformations would be. So I've found it helpful to start by looking at what you find to be different. What do you see that's different in the new function that's not in the parent function? Well, if the parent function is x squared, we're going to have to deal with this 3, and we're going to have to deal with the negative 2. And as we briefly talked about previously in Learning Target 2, what really is helpful, I think, is to think about in what order some number you were to input for x would encounter those numbers associated with transformations. So if I were going to find like g of 4, for example, I would put 4 in for x, and the very first thing that would happen to that 4 is it would get subtracted by 2. So the fact that that would happen first says that I need to deal with that first. What would subtracting 2 from the input of a function do? It would shift the graph not left, but right 2 units. One of the things that was mentioned previously in your notes is the idea that, in general, anything that happens to the input itself, anything that happens directly to x, does the opposite of what you would expect it to do, and it does it to the x coordinate. So a shift right or left in this case. Once that number was subtracted by 2, we would square it, and then that number would finally be multiplied by 3. So multiplying the function by 3 is going to, you could say it's a couple of ways. I'm going to say it multiplies each y value by 3. You could also say it stretches the function vertically by a factor of 3. I kind of find this notation helpful because that kind of describes literally what you do to make the graph of the transformation. And we've dealt with everything, so we've got it. Okay, this one's for you to try. See if you can describe the sequence of transformations that transform this parent function, the reciprocal function 1 over x, into this function. Well, what looks different in g of x than it did in f of x? You've got 1 over x here, you've got something over x, but it's not 1. So that's something. And the plus 3 is something, isn't it? In what order would some number put in for x encounter those? If you were going to find like f of 2, or rather g of 2, you would let x be 2, and then you would have to take the negative 5 and divide it by the 2. So this is first. You know, it might be helpful to think about this. Function g of x, not as negative 5 divided by x, but maybe it helps to think of it like this. Negative 5 times 1 over x plus 3. You find that helpful? I do, because I think it makes it clearer to tell exactly what that negative 5 does. Written this way, that is negative 5 times the original function itself, which tells me that we're affecting the y values. We're going to multiply each y value by negative 5. So once we took that number 2 and multiplied the negative 5 by 1 over 2, then finally we would add 3. And that's happening to the function itself as well. So that will shift the graph up 3 units. Okay, this one's for you as well. This time work with the parent function, the absolute value of x, and see if you can find a sequence that will transform that into g of x. G of x in this case has not 1, not 2, but 3 things to deal with. To find a sequence that will turn absolute value of x into 2 times the absolute value of x minus 3 plus 1, I've got 3 things to do. Which one's first? Yeah, it's the minus 3. And it's happening directly to the x. You know, it's inside the absolute value notation. So that minus 3 is happening just to the x. That means it's going to shift the graph right 3 units. So after we take some number and subtract 3, we'd find the absolute value of that number. What's next? Yeah, we would multiply. So the 2 is second. The 2 is multiplied not by the x, but by the function, by the absolute value. So it's going to multiply each y value by 2. Or you could say it stretches the graph vertically by a factor of 2. The very last thing that happens to the function itself, we add 1. So that will shift the graph which way? Added to the function itself, it's up 1 unit. Okay, one more here for you to try. See if you can transform f of x equals the square root of x into g of x. How'd you do? This is a great example of where the order of the operations makes a big difference. I've got this. This one in green. And this in the red to deal with. So if I put some number in for x, the very first thing it would encounter is the plus 2. Now, I could see where maybe you might have distributed that 3 into the binomial x plus 2 and written this as the square root of 3x plus 6, and that would work. I don't think there's a reason why you necessarily would need to do that here. I think that's creating work that makes the problem a little more complicated. So let's do it like this. Let's say if we add 2 to just the x, we're going to shift the graph left 2 units. Then once I add 2 to the number, I'll multiply the input to the function. The x, the input, not the square root, but the input, by 3. It's tricky. That divides each x by 3. It's a great example of that doing the opposite of what you might expect idea. And then the very last thing after we find the square root of that number is to subtract pi from it. So since it's happening to the function, this will shift us down pi units.